Okay. So, in the discussion of the hybrid learning algorithm, we mentioned I mentioned that we need the k-means algorithm to compute the cluster centers, and then I talked about the inversion issue that we have, which is going to be difficult when we have large size of these data sets. When we have a lot of data points, then inversion becomes a problem. So, we require an adaptive algorithm to overcome this inversion issue, and this can be done via the recursive least squares algorithm. This is one of the standard algorithms in adaptive signal processing, but I will discuss this technique here as part of this problem, so that this tool will be very useful for you in your solution when you deal with practice. Okay. So, recall that this matrix capital R times this vector W equals this vector small r, where we have defined all these terms earlier in our slides, right. So, I will just recall again. R as a function of the time index small n is summation I equals 1 to small n phi of xi times phi transpose of xi, where phi of xi equals this phi of xi comma mu 1, that is my first coordinate, dot 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 phi of xi comma mu suffix k transposed right. So, I have k different means mu 1 through mu k, and I evaluate this data point over this function phi function which has these arguments as the cluster means. Okay. So, if you recall my in the matrix R that I had, I never mentioned about R of n, R of small n. I mentioned this capital R equals summation I equals 1 to capital N, right. If you just recall, I mentioned this equal to summation from I equals 1 to capital N here, but we do not have to be restricted. We will do this estimation as we get these data points online. So, therefore, we can say that this is summation I equals 1 to small n phi of xi times phi transpose of xi. Now, just to recall, our phi of xi comma mu j equals exponential minus 1 upon 2 sigma j square the norm of xi minus mu j square, right, and j runs from 1 through k consistent with our clusters. So, k is the number of clusters. Now, the k by 1, I call it the cross correlation vector. This is given by small r, which is a vector small r of n, which is summation I equals 1 to n phi of xi times d of I. You can call it d subscript I, or you can call d of I, does not matter. So, just to indicate carefully that this is the desired response at the output of the radial basis function network, and phi of xi is the hidden response. Now, w hat of n needs to be optimized in the least square sense. Why? Because R inverse is order n cube complex, because inversion is having complexity on the order of n cube, where n is the number of data points, and difficult. It is computationally difficult. So, this motivates our purpose, that is, we need an algorithm to overcome the inversion issue towards computational efficiency. And in general, this is a problem why we need adaptive algorithms in most cases. Yeah, before I end the slide, a small detail, R is of dimension k by k, right. It is not n. I just wrote it at order n cube here, but to be slightly more precise, it has to be inversion of R is order k cube, because if you look at this phi of xi times phi of xi transposed, you have a k by 1 times a 1 by k, which is a k by k matrix, and you are stacking up all these k by k you are adding all these k by k matrices, right. So, therefore, this inversion has to be order k cube, I mean consistent with the size of the matrix that we have here. So, let us proceed with the details. Now, R of n equals summation I equals 1 to n minus 1 phi of xi di plus, I will use this d of I, plus phi of xn times d of n, right. I am just splitting it in this form. I mean, if you look at the original summation, it is summation I equals 1 to small n phi of xi d of I. I will just split this into the first n terms, summation from first n minus 1 terms, and then the last term. So, now this can be written as R of n minus 1 plus phi of xn times d of n, right, and this is my R of n. Now, fortunately, I know the solution for R of n, which is in terms of capital R and in terms of the weight vector. So, I can do this estimate for small r of n minus 1, and using this idea I have R of n minus 1, capital R of n minus 1 times estimate at time step n minus 1 plus phi of xn dn. So, this is straightforward. Now, I can also express R of n minus 1 through a recursion, right. So, let us expand R of n minus 1 further. So, we have R of n equals so before I think before expansion I would say we can add and subtract some terms so that it helps us slightly carefully. So, what I will do is as follows. I make this R of n minus 1 plus phi of n. So, I will throughout let me do this. Let us subsume x n in phi of x n, this data vector x n as phi of n. So, when I mean phi of n, it implies that it is evaluated at x n. Okay. So, because I have to write this x n throughout and carry this forward. So, I will subsume this in this form. So, my vector R of n is this. So, what I do is I add phi of n, phi transpose n into this term. In that way I am sort of expanding this out here, w hat of n minus 1 plus, since I have added this I have to subtract it, and what I do is I take phi of n times this is d of n, phi of n, d of n is the way it is, but I subtract phi transpose n w hat n minus 1. So, there is a vector here and there is also a vector for phi. So, and d is a scalar. Okay. So, I am just adding and subtracting phi n times phi transpose n times w hat of n minus 1. So, this is what I am doing. Okay. Yeah, we need to put this bar here for w hat, just a small fix. Now, we also have a recursion for R of n, capital R of n. So, capital R of n is capital R of n minus 1 plus phi of n, phi transpose of n. So, you have to be careful here that this x n is sort of subsumed as index n, and I can avoid that x that repeats throughout the equations. Now, let us define alpha n to be d of n minus phi transpose w hat of n minus 1. And I can, because this is a scalar, right, phi transpose times w hat is the same as w hat times phi transpose. So, I can always write this in this form, w hat n minus 1 times phi transpose. There should be an n here. Okay. There should be an n here. So, we get this in this form. Now, this term alpha n is referred to as innovation. It is called an innovation, it is called the innovation term because we have a prior estimation error based on old value of w hat and given the current response dn and and what we have with phi n, using the prior estimate of w hat we compute this term. That is why it is called innovation, because this is over the prior estimate on w hat. Now continuing, r of n, the small r of n is capital R of n times w hat of n minus 1 plus phi of n times alpha of n, right. Alpha is this scalar, phi is a vector, and everything is consistent. Okay. Now this small r can be written as capital R of n times w hat of n, and this is equal to r of n w hat of n minus 1 plus phi of n alpha n. So we can say that our update w hat of n equals, so if I just multiply, pre-multiply this equation here, right, I just call this equation 1. If I just pre-multiply equation 1 by r inverse n on both sides, I can simplify this to be in this form: w hat of n equals w hat at time step n minus 1. So there is a vector here plus r inverse of n phi of n times alpha n. So this is the update rule. On the slide here, w hat has to be transposed and this is phi of n. So that this is an inner product and we have a scalar, just a small typo to be fixed here, right. You may wonder again, what is it that we have here? Still we are dealing with this inversion. What have we simplified, right? Fortunately, we can invoke the matrix inversion lemma that comes to our rescue to compute the inverse given certain parameters, and we will set this up. So to solve for R inverse, appearing in the update rule, we invoke the matrix inversion lemma. So if you go through any book in linear algebra, you will find this result. Now here is the statement. So consider the matrix A equals B inverse plus C times D times C transpose. I will define what these values are. assume that this is possible, that you have these matrices that commute in that can multiply, that can give you this result which is consistent with the matrix multiplication rules. So, A inverse can be computed as B minus B times C times this term which is D plus C transpose B times C times C transpose B transpose. This is the result. So, if I have matrix B and these other matrix elements C and D which form the matrix A in this form, that is B inverse plus C times D times C transpose, then we can compute A inverse in this form. So, for our setup, A is this matrix capital R of n, B inverse is this R of n minus 1, C is this vector which is phi of n, and D happens to be 1. Yeah, we missed an inverse sign here on this slide. So, we need to put that so that this is correct. Now, so plugging in R inverse of n. Now, B inverse is R of n minus 1. So, B is basically R inverse of n minus 1, R inverse of n minus 1 minus R inverse of n minus 1 times phi of n. P is basically R inverse of n minus 1, then we have C to be phi of n, which is what I have written down, then D is 1 plus C transpose is phi transpose of n times R inverse of n minus 1 times phi of n. So, this inverse times C transpose times B transpose, which is basically phi transpose n times R inverse of n minus 1. Okay. So, this is just plugging A, B, C, D in this inversion formula. Now, simplifying this a little further, we get R inverse of n minus 1 minus, now this is basically a scalar, right, 1 plus phi transpose n times R inverse of n minus 1 times phi of n, and that is basically it gets into the denominator. So, I get minus R inverse of n minus 1 times phi of n times phi transpose of n times R inverse, there should be a transpose here, right, B transpose. So, B is R of R inverse of n minus 1, there should be a transpose here, this previous I just put a T here. So, inverse transpose of n minus 1 upon 1 plus phi transpose of n R inverse n minus 1 times phi of n. Now, let us define this matrix P of n to be R inverse n because I want to get rid of these inverses somehow. So I define like this, and R transpose, we have this property R transpose of n equals R of n. So this justifies that the inversion transposed is basically P of n minus 1, right. So therefore R inverse transpose of n minus 1 is same as R inverse of n minus 1. So therefore we can write it in an easier way, right. So R inverse transpose of n minus 1 is R inverse of n minus 1, which is P of n minus 1. So let G of n be defined as this term, which is given by R inverse of n times phi of n, and I call this the gain vector. So the gain vector G of n can be written as R inverse of n is basically P of n times phi of n. So therefore our update W hat, so we started off somewhere much before here, that I wrote W hat of n is W hat of n minus 1 plus R inverse n phi n times alpha n. So R inverse is basically P, and P times phi is this gain G, and gain vector times the innovation is what I need to have here. So W hat of n is W hat at time step n minus 1 plus the gain vector times the innovation. So just have to make sure that I have all these underscores for these vectors that I do not miss. So okay, I had missed one here, so we have this complete. So I think this is the update, and with this we are ready to summarize the algorithm for recursive least squares. So let me summarize the algorithm so that it is easy for us to compute. So what we are given is the following: we are given these phi I and di. I know the desired response for the radial basis function for each of these inputs, and I know these functions evaluated at the data points xi, and that is phi of I. So do the following. For for n, I would say for small n, time step equals 1 dot 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 till capital N, you do the following steps. So I will talk about initialization towards the variant. So here is what you need to do: P of n is P of n minus 1 minus P of n minus 1 times phi n, phi transposed n times P of n minus 1 upon 1 plus phi transpose n times p of n minus 1 times phi of n. Compute the gain vector g of n to be p of n times phi of n, which is this vector. Compute the innovation alpha n to be d of n minus w transpose of n minus 1 plus times phi of n w transpose of n minus 1 times phi of n is a scalar here, and then the update w hat at time step n is w hat at time step n minus 1 plus the gain vector times the innovation, which is alpha n, which is basically a scalar. So, this is a scalar and this is basically g of n is a vector. Now, you would wonder how do I start, because the recursions are with respect to w hat of n, because there is a recursion there, and p of n there is also a recursion because it depends on p of n minus 1 plus these terms. So, to initialize, so we need to set the following: set w hat 0 to be this 0 vector, and p of 0 is this matrix which is initialized to lambda inverse times I, where lambda is a small positive constant. Okay, and these are some basic steps. So, once we initialize, then I think we can begin with these recursions. So, I have phi I and d sub I that I can compute. D sub I know for all the data points, that is a desired response. Phi of I, which is basically phi of xi, is what I can compute given all the cluster means. So, from this I can set up to computing p of n, which is basically R inverse n. I can compute that using this recursive equation, and then I compute the gain vector, the innovation term, and then the update rule for w hat, which depends on w hat of n minus 1 plus the gain vector times innovation. Okay. This is an important procedure and it helps simplify a lot. Fortunately, it works because we have an elegant result from the matrix inversion lemma, and that has helped us simplify towards this algorithm. Okay. So, to summarize in a nutshell, the hybrid learning procedure requires first to get the centers, because you have to decide the number of radial basis functions, and the choice of that can come through clustering of the data. So, you can do some clustering a priori and get the cluster means, and that can be done through the k-means algorithm. And then there is no much difficulty because we have to solve for the weights connecting the layer having these radial basis functions with the output, right. To solve for the weights, we require inverse of a matrix that depends upon the basis evaluated at the data points and the cluster means, right. To overcome this inversion issue, if it is a simple network with just 3 basis functions or 4 basis functions, then we have no problem, right. 4 data points, 4 basis functions, absolutely no difficulty, we can just compute the inverse, not a problem. But this is typically not the case, because we have a large number of data points for which you will have to do this inversion, which is going to be hard. So, therefore, we can go in this route by invoking the RLS algorithm and then solving. Okay. So, this should complete the algorithmic summary for the radial basis function, and I hope you can try this algorithm over some data sets and get a feel for this procedure. Okay, we stop here.